Welcome to Ido's video channel. In this video, I will take you through the tank sizing process for water reticulation networks. In this case, I have a water reticulation and I ran the peak flow analysis to do the pipe sizing. And as you can see here, I used Reservoir as an infinite source of water, but for the tank sizing, I need to swap it to a tank because when I did a peak flow analysis, I was not really interested into the water source and how big it is, so I used the Reservoir. I could also use a tank with a very big diameter, which would also serve as an infinite or almost infinite source of water. What I did as well, I created a profile view because in this case I have an elevated tank or reservoir, so it is above ground, maybe about 8.5 meters above ground. And I want to now run the tank sizing and find out whether the tank will suit this network. Let me open the pipe manager because I want to show you how I set up the entire network or what values did I use for the peak flow analysis. I'm going to structures, and then for the reservoir, I use the water depth of 1 meter. So 1 meter in a reservoir, and then it flows into the system. If I go to fire hydrants, I'm using 25 liters per second, but I'm not using all of them at once. I'm using patterns to open one fire hydrant at a time. I will explain that a bit later. When I go to sewer house connections, I use the demand and no pattern because when you run the peak flow analysis in IDAS, it will create patterns for you, and these patterns open or close specific structures. For example, if I go to pattern number 1 for house connections, at time 0, there is no demand, so multiply is equal to 0. At time 1, it opens, so the demand is there for the house connections, and so on. But if I go to, let's say, fire hydrant 1, it is closed at time 1 and time 2. It only opens at time 3, which means that at time 0 there is no demand at all. At time 2 there is only house connection, or there are only house connections, and at time 3 there are house connections and fire hydrant 1, house connection and fire hydrant 2, and so on. But this is not something I want to use for tank sizing. For tank sizing I need to use proper pattern throughout the day because I want to find out whether the tank is big enough. And now when I go back to structures and the direct demand, I used 0.065. Where did I get this value from? Let me drag over my spreadsheet. This is normal Excel spreadsheet. I just open it in a LibreOffice because LibreOffice has a little bit better dark theme. And here let me explain you. For my area, or for this calculation, I used South African Red Book, but any other standard can be used. There are some discrepancies between those standards, but the logic is the same. So for my stands in this very simple layout, and they are fairly the same, I have average annual daily demand of 1000 liters per unit per day. Then I have some losses in the system. I estimated them to be 22%. Generally, they are between 15 and 25%. Then, if I add those two values together, I get a total annual average daily demand, TAADD, which is in liters per unit per day, 1220 liters per unit per day. Then from that, I calculate the total average hour demand, liters per second. So it's very simple calculation. It is this value, which is per day, divided by 24, which is per hour, divided by 3600, which is per second. And this value is the average demand. And for the peak flow analysis, I multiplied by the peak factor. And for my area, peak factor is 4.6. So the total peak hour demand per unit is 0.065. And if I go to my settings, I'm using here 0.065. And for the double house connections, I'm also using that value multiplied by 2 because I have a double house connection. So these are the values I used for the peak flow analysis. But I can't use these values for the tank sizing because I need to use a different values. Let me drag over that spreadsheet I used before. And now I need to calculate the tank required supply rate, the inflow into the tank, which I need to provide. Now what it should be, there are various approaches how to calculate the value. I used the following approach. I calculated number of single house connections, number of double house connections, and then based on those two values, I calculate number of units or parcels. Then I calculated what is the total average hour demand for all the units. This is a very simple calculation. I just multiplied the number of units by total average hour demand, and I got 0.48 liters per second. Then I need to specify the peak factor per day. There are various peak factors for week, day, or hour. In this case, they suggest using the peak factor for day. In some other cases, you might use another approach. For example, they require that the pump that supplies water into the tank must operate only in the night because the electricity is cheaper, or during the day because it allows you to use a smaller tank. Because if you pump only during the night, for the day you need quite a big tank because it must supply the water for the entire day. If you pump during the day, then you can cover those peak demands with a pump. Then I calculated the value, which is basically the total average hour demand multiplied by peak factor, and I got about 1.056 liters per second. And I rounded it to 1.1. So basically I want to supply tank with about 1.1 liter per second. This is a very small area. It is a very small inflow or supply rate, but let me use it for my calculations. Then I need to calculate the tank balancing storage. In this case, I decided that the tank should cover 12 hours of the demand, and that yields to this value, which is about 20,000 liters. How did I calculate it? So it's very simple calculation, because I multiply the number of units by total annual average daily demand, which is per day, divided by 24 per hour, multiplied by 12 hours. So in an average 12 hours, I will need 21 cubic meters. So that's a balancing storage for the tank. But there's also a requirement that I need to cover the firefighting storage. And in this case, I need 25 liters per second for a fire duration of 1 hour, which is 3,600 seconds. And that provides me a requirement of 90,000 liters, which is 90 cubic meters. If I sum those two values, I get 111 cubic meters. In this case, the firefighting storage is probably 80% of the total tank storage. Because the area is very small, I have only a few parcels. But if there is no any other water resource that can be used for firefighting, then there must be available volume. And for this total tank storage volume, I need to find out a suitable tank. I keep it very simple for this exercise. I'm using circular tank, but you can use a spherical or double ellipsoidal tank or any other shape that suits your needs. If the tank diameter is equal to 6 meters and the tank height is 4 meters, then it provides a volume of 113 cubic meters, which is higher than this value, so this can work. I also calculated the fire volume depth, because that's the minimum depth I can go to make sure I always have enough water for firefighting. So I cannot go below 3.2 in my tank. This is a very simple calculation. Again, you just calculate the water level if you need to store 90 cubic meters in this tank. So this is a very basic calculation. And now let me model everything properly. I will move back to Civil 3D and IDAS. I will close this manager because I need to readjust the pipe network. I will add a branch with the source of water, which will flow into this tank. I need to swap this structure to tank. So let me do it as a first thing. I go to swap structure, then I select the structure and I use a tank. Okay. And I will change the name. So I go to structure properties, and as a name, I will use tank T1. Okay. Then I go to edit network. As a structure, I select reservoir, and as a pipe, I will use Aquaflow HDPE PN10 100. I will use a diameter 50 millimeters. And then I go to design. It doesn't allow me to select pipes and structures, but hopefully it works. So there's a reservoir. Then the following structure will be junction. So let me go there, junction, and I continue to this point, and I go up to that point. It didn't create pipes because for whatever reason, this command doesn't allow me to create pipes. So what I need to do, I need to close this drawing and reopen it quickly. So let me do that. And let me try that again. I go to Edit Network. And this time I will select again the Aquaflow HDPE PE100 PN10 50 millimeters. Since I already created the structures, I will use a pipes only, and then I will go from here to there and to tank. As you can see, by accident, I created this structure because I had some difficulties with Civil 3D. Unfortunately, that sometimes happens. But now I designed everything nicely, and what I'll do, I will adjust the alignment because I want to see the entire branch from the reservoir to tank. So I go to Edit Alignment Geometry. Then I will highlight those structures because I want to use them as an insertion point for my PIs. Let me do that now. I'll need to stretch this alignment a bit so I can drag it. I will switch off the snapping because I want to make sure it snaps to the grip point, and I will select this structure as well. I go to Insert at this point and this point. So now the alignment is adjusted. I can close the Edit Alignment Tools toolbar. And then I go to Profile View because I want to check the levels. It looks very weird here. I will use IDAS because I want to clean up Profile View. And for this Profile View, I want to display Water Network OK. That looks definitely better, and I can start adjusting. I want this pipe to have invert elevation aligned with the outgoing pipe, so let me do that. And this is the outcome. I also want to adjust this portion. I can do it by eyeball, or I can use the IDAS tools to make sure I'm specific distance below ground. I don't like it here either much, so I will move it a little bit to the ground so I have some cover. And I don't like the way it looks here, so I'm going to Insert Structure. I will specify the network, the surface, junction, and I want to use a cover 0.8 or 1, OK. And I will position it somewhere here. Yes, I want to reference them, and that looks better. So I have elevated tank, and I have a source of water, and then I pump it up. I need to insert pump somewhere here. So I go to Insert Structure. I will use a pump. 1 meter or 0.8 below ground. OK. And I will specify the location somewhere here. So I have a pump. I will rename the reservoir. So I go to Structure Properties, and I will call it Res1. Res1 as a reservoir. And the pump structure properties I will call simply pump. OK. So I have a reservoir, pump, and then I have tank. Let me go to Plan. I will rename those pipes to make sure that they go nicely. If I look here, I think I named those pipe P2.1, 2.2. Let me go there. Yes, this is 2.1. So I will go, you don't need to do that. That's just for myself because it's easier for me when I run the analysis. So I go to Pipes, Utilities, Rename Network Parts, and I will go from reservoir to tank, but I will rename only the pipe, no structures, and I will use a 1.1, and if there is a conflict, I want to rename existing parts. OK. And now everything is renamed properly. Let me open Pipe Manager. And I'm going through the structures. I will start with a reservoir, and for the reservoir I will specify that at the beginning I have a 2 meters of pressure. And that's it, I don't need to change anything else. Then I go to tank. And this is a cylindrical tank. There's an invert elevation, height above surface. Normally, we very often just let the water to flow into the tank. If you don't do any settings here, it will flow at the bottom of the tank. But I want to have atmospheric inflow here. How do I model it? Under the inlet position, I will set it to top. As soon as I do that, it requires inlet elevation for me to set up. If I come in here, there's an invert elevation 1.485, and inlet elevation of this incoming pipe should be above that. And if I know that the water level should be 4 meters above, so I need at least 1.489. So let me copy this to clipboard. I will paste it in here, but I will change it to 489. But I will add another, let's say 10 centimeters, because I want to be a little bit above maximum water level. So this will allow me to have an atmospheric inflow into my tank. Initial water depth. I will start at a depth of 3.2. So when the tank has enough water for the firefighting, that's my initial water depth. Minimum water depth, I will go to 0. Sometimes they require that there should be at least some amount of water in a tank, but I will go to 0. Maximum water depth, I will use 4 meters as per my calculations. Let me show you that spreadsheet again. Tank diameter 6, height 4, fire volume depth 3.2. Those are the values. Initial water depth, and I don't want to go below this depth. Minimum 0, maximum 4, tank diameter 6, like that. Let me go to pumps. Then outgoing pipe should be 1.2. If I look here, 1.1, 1.2. Then under the pump curve, I need to define pump curve. Normally, you need to run system curve analysis to find out the suitable pump curve. This exercise is about a tank sizing, so I did it beforehand. Let me import pump curves. I'm going to Library, Curves, Import Curve, and I will browse to my desktop where I have a pump curve. Open, and this is pump 1 curve, which has the following values. Let me go back to structures, pump, and I assign the pump curve, pump 1. Then I need to specify the speed multiplier 1. But with this setting, the pump will always run. And I don't want that. I want the pump to only run if the water level is between 3.2 to 4. How can I do that? I will introduce controls. I'm going to Library, Controls, and I will add a new control. And here I can specify if structure tank T1 level is below value 3.2, then pump speed multiplier is equal to 1. So if the water level is below 3.2, the speed multiplier is equal to 1. I will make a copy of this control. And if tank T1 level is above 4 meters, then the pump speed multiplier should be equal to 0. So basically pump will be closed. Those controls will automatically be used during the analysis, so you don't need to assign it anywhere. So just define them. Let me go back to structure, pump. So pump will not run all the time. It will only run when the specific criteria are achieved. I have some valves, but basically those are gate valves. I'm not going to do anything with them. Then I go to fire hydrants. For this type of analysis, we have a volumes for firefighting, so I don't need to do anything with the fire hydrant. So let me specify the demand to be equal to 0. Okay, then I go to single house connections. And if I drag over my Excel spreadsheet, you can see that I should use 0.014. Let me move it back, and I'm selecting both. Edit value, demand, 0.014 for the single house connections. But I also need to assign the demand pattern during the day. For that purpose, I go to Library, Patterns, and I go to Import Patterns. Those patterns which you see here are from the peak flow analysis. You can keep them there, but I go to Import Patterns. And if you go to Application Plugins, Devotech.bundle, Content, Support, Design, Storm Patterns, there is a water demand pattern. By accident or by mistake, it is under the storm. We will move it to water. If you go to Design, Water, it should be here. But as I said, by mistake, it is under the storm patterns. So use that 24-hour water demand pattern. But for your area, you might need to use a different pattern. This is just an example. Let me open it to show you what it looks like. Let me select it. I will change the name. I will call it demand. It's a water time, 24 hours. And here you can see the patterns during the day. Don't get confused. If I show you here, the peak factor per hour is different and peak factor per day is also different. So those values might not correspond with this maximum value. Don't get confused. So now I can assign this pattern to single house connection. So let me do that. I go to Edit Values, Demand Pattern, and then I will assign demand. Okay. Let me go to double house connection. Again, for all of them, I will adjust the demand. It should be 0.014 multiplied by 2, which is 0.028. And then I need to assign demand pattern. Let me go to Edit Values, Demand Pattern, and I will use demand. Okay. Now I go to Conduit, and I have some new pipes. If I sort the pipes by roughness coefficient, you will see that some new pipes do have a 0 roughness coefficient. So I will change it to 0.0015, and I can run the analysis. I will run the normal analysis. I can just analyze, or I can go to Analysis and Analyze. Then I click OK, and I check the report, because under the analysis report, I can see if the analysis was successful. And here I can see the hydraulic status. If your status looks different, you can change the status report to either full, none, or yes. I'm using yes, which is easier to read for me. And I can see what's happening here. The reservoir at time 0 is emptying. Tank T1 is filling. The pump is pumping. At time 8:50, the pump is changed because of the T1 control. And reservoir is closed. Tank T1 is emptying at level 4 meters, and pump changed from open to close. And then the pump is not running, and I'm using tank to deliver the water. And at time 9 o'clock and 1 minute, again, there's a change, and I'm starting to pump. Let's go to graphs, because that might be a nice place. I will sort it by type. Let me select tank, and I will display pressure. And I can clearly see what's happening. So at time 0, when I start the analysis, I have a pressure of 3.2. Then I'm pumping, but also using the water. And at the time of 9 o'clock, I'm reaching the pressure of 3.9, almost 4 meters. And again, it goes like that. Maybe it would be more practical to see a little bit longer time period, and sometimes there's a requirement that you should run it for a week. So let me go to time and energy. And for the end analysis date, I will change the value. Let's say I will run it for a few days. And let me run the analysis, normal analysis, not a peak flow analysis. Okay. And here you can see the result. The pattern looks very similar. There might be slight differences, but basically the water level in the tank is between 3.2 up to 4 meters, because my controls are controlling the water level. Let's display another graph. I will display reservoir, and for the reservoir I want to display demand, because this shows me how the demand is used. I will stretch a bit the graph, and then I will turn it back so it refreshes the view. And you can see here at that time 0, I'm taking water from the reservoir. The amount of water is minus 1.1. And that's what I'm drawing from the reservoir. And then when I reach this elevation, it stops. There's no demand. And again, and here I can see, for example, at some situations, it might be running for longer. For example, here from 85 to 94. So it's about 9 hours. So the pump is running for about 9 hours maximum. Here is probably the same, 109 up to 100. Yes, 9 hours again. So I was targeting for somewhere around 12 hours maximum. In this case, the maximum is about 9 hours it's running. And then let's display some other graphs. I'm going to conduits. And for the pipe, let me go to plan. I want to see the flow through the pipe P1.3 and P2.2. I want to compare them. 1.3, 2.2. So I go to graphs, conduits, 1.3. I want to display flow. And 2.2, I also want to display flow. Let's adjust it a bit. And here I can see the pipe 1.3, which is flowing from the reservoir to tank. You can see there's a flow, there is no flow, because it corresponds with the graph for the demand from the reservoir. And then the pipe, which is supplying water to the system, to the parcels, you can see based on a demand pattern, it goes up and down. And that shows me how the water is drawn from the tank. Let me go to profiles. I would like to display hydraulic and energy grade lines. I will select reservoir and then I go to set as a profile start structure. And this is a hydraulic grade line. If you don't see hydraulic grade line, let me go to view and there's an option to tick that on. Then I go to ribbon home. I will update the results to Civil 3D. Let me update. And let's go back. And this is the result. But there are two things I don't like much. This line goes from the pump and it pumps this pressure, but it displays maximum at the first node. So if I want to improve this view a bit, then I go to insert structure. For water final surface, I will use a junction and I want to interpolate structure depth from current pipe slope. Okay. And I will place it somewhere here. That will display a little bit better, but I need to rerun the analysis because it doesn't show the hydraulic and energy grade line for this new pipe. This pipe is newly created because I split the existing pipe. And there is the other thing which I don't like much. I don't know why it is like that, but I know that Civil 3D sometimes when I go to pipe properties, it uses various flow direction method. And for water reticulations, we always use bidirectional. Okay. And I'm not sure about other pipes. Let me go to pipe properties. If it is bidirectional, also start to end. So I should probably change it for all the pipes. So I go to IDAS, water, swap direction. And for the selected pipes, I will select probably all of them in a profile view. I want to set the flow direction method to bidirectional. Okay. Let's double check if it is set correctly. So I go to pipe properties, bidirectional, and let me double check the other one, pipe properties, bidirectional. That all looks good. This newly created pipe might have a different name. It's P79, so I can call it P2.1.1 or whatever is suitable. And let me open the pipe manager and rerun the analysis. I can just rerun the analysis, but if I do so, I might get the error message because I didn't set the roughness coefficient for the new pipe. So I'm going to report, analysis report, and you can see pipe 2.1.1 contains illegal numeric values. So I'm going to conduits. I can sort by roughness coefficient, and I will use a value 0.0015. I will rerun the analysis. Okay, I go to profile and I will again select the reservoir, set as a profile start structure. This looks definitely better. Let me go to home, update results to Civil 3D, update. And this is the result. So as per my graphs, I could prove that the tank is working. The water never reaches below 3.2 or above 4 meters, and the pump is delivering enough water, and it runs in average, let's say, 6 to 9 hours. I can also display flows and velocities. This pipe delivers about 1.2 liters per second with a velocity of 0.8, and then further down these values are not that good because those pipes are designed for the peak flow analysis, and I don't have a fire hydrant open. The velocity is 0, but it's not in fact 0. It's very low because there is some kind of flow, but based on a diameter which is 180 millimeters, it's close to 0, so that's why it shows 0. Maybe that can be solved by displaying more number of decimals. But as I said, these pipes are designed for the peak flow analysis, while I'm using here just the house connection demand, which is very low demand. If I compare it with a fire flow, which requires 25 liters per second. This is a small area, only few parcels, so that's why the firefight demand is quite high in comparison with the house connection demand. So this is basically how to deal with a tank sizing. Very briefly, I didn't go in detail through the equations and all that because you might be using different standard, but at least you know how to make sure that the tank is working for your design.